Okay, now I've got a formula for velocity, and if I were to plot velocity against time, I'd get this sine function. Look a bit like this. Time against velocity. What is it about that function that tells me the acceleration?
The angle on the line.
Yeah, the gradient, in other words. The gradient of the line. Right, well done. The gradient of the line tells me the rate of change of velocity. In other words, if I want to get the acceleration, I've got to differentiate this. What's the differential of this function? So I look at the minus r omega sine omega t and differentiate that. Sine becomes cos, and the omega comes out. So we get minus r omega squared cos omega t. But we know a formula for x. So I can replace the r cos omega t with x. And I get that the acceleration, which is the rate of change of velocity, equals minus x omega squared. Again, the sign is just to do with the fact that this acceleration is sort of acting as a restoring acceleration, if you like, trying to slow it down. Another key formula. When is acceleration greatest? Sorry? And when is the velocity zero? Furthest from equilibrium. Yeah, at its furthest point here, at the furthest point from equilibrium, we get maximum acceleration. And if we think back to this diagram here, that's this point here, the furthest point. This is x up and down here. So the furthest point from equilibrium, in other words, when x equals r. So when x equals r, the radius of rotation, if you like, then we get maximum acceleration. So we can just add another little formula here and say that A max is minus r omega squared, or r omega squared if we want to just get the value. We're only interested in the size of the acceleration, not which direction it's acting in, which is usually the case. So that's some formulae that are going to come in really useful when doing questions.